Hello, Calc 2 students. This is our last lesson for the year for our e-learning we're doing in 2020 here. So we're going to do polar coordinates, and I'm going to do this on Desmos rather than the .cam because there's a lot of crazy graphs to show you here. It's pretty cool. And also I'm going to show you some tools in Desmos. So first off, I'm going to change the grid over here under settings to a polar grid. And what this means is that when you graph a polar point, you are trying to rather than thinking about x and y, walk over here, then walk up, you're trying to think about you're standing in the middle of the coordinates, turn a certain angle, and then walk out a certain amount, which is the radius. So our points are going to have an angle and a radius, but alphabetically we're going to put the r before the theta. So it's going to be the radius, how far to walk out, and then the angle. But when you're thinking about how to move, stand here, turn where you should turn, and then walk out. So the first part says plot the following points in the plane, and it says r is 1 and then theta is pi over 4. So plotting is a little annoying in Desmos because if you do this, it thinks that's not the right spot because it thinks you mean, it actually looks close to the right spot, but it thinks you mean rectangular coordinates. So the actual spot, let's get rid of that dot, would be, so this angle, they're not marking it very well, but here's pi over 6, here's pi over 3. This should be pi over 4 right here, and the radius is 1, so it would be right there, right where my cursor is. But there's not an easy way to plot that in Desmos. I'm going to come back to that point and we'll convert these to rectangular, and you can see the point. But yeah, that was the wrong spot. It's right there, not the green dot. Okay, the next one says 3 comma pi, so I would go to pi, so 180 degrees, and then go out 3, and that's that spot right there where my cursor is. That one's an easy one to see what it is in rectangular, right? It's on the axis, so it's minus 3, 0. And that's rectangular coordinates, and we'll have a plan for converting here in a minute, but in polar coordinates, go 180 degrees, and then from the center, walk out 3 units. Okay, the next two are 0 pi over 12 and 0 pi over 7. And again, I'm on the workbook on page 62. Notice the two different angles, but a radius of 0. They're both at the origin. And it's because the radius is 0, so you don't have anywhere to go. The weird part about polar coordinates, one of the couple weird things, is that they're not unique, unlike x and y. I can have any angle with 0, and I can have that same spot. I can also, if you look at the next one, it has -2 and pi over 6. So that's a couple ways to write the same spot. So how does that work? Well, you go to pi over 6, you're at the center, and then rather than walking this way 2 units, you walk the wrong direction. That's what -2 means. Another way to mark this point here where my cursor is would be to go all the way around pi, then another pi over 6, so 7 pi over 6 with a positive radius of 2. So there's actually infinitely many ways to mark each point. Okay, so in your workbook, it gives you some equations that are going to make no sense here in Desmos, so hopefully they won't graph. But it says here are the ways that you convert between the two, and we'll do a couple conversions here. Tan theta equals y over x, and then x squared plus y squared equals r squared. And I do not want a slider for r. These are the 4 equations you're going to use to convert, and you can see if you have a polar point, it's pretty easy to convert to x and y because you just plug and chug. So if we go back to that very first point, it was r equals 1, and theta was pi over 4, so it was right here. Well, then that would say that x is 1 cosine pi over 4, which is that value. Don't ignore the graph there. And then y was 1 sine pi over 4. Okay, I get those two values, which hopefully you recognize those as root 2 over 2. So the point then is square root 2 over 2 over 2. Square root 2 over 2. Okay, so that's the point that we talked about, right? If you go pi over 4, and then you walk 1 unit from the center, you get that red dot. And what I've written is I've written it in rectangular coordinates. So in general, plugging in r and theta, not too bad. Let's do another one. Let's do that last one that had the negative radius. So if I did, get rid of this dot, if I put -2 here and cosine pi over 6, I would get that value, and then -2 here and sine pi over 6. Hopefully we'll get the right dot. So that says that x should be negative, what would that be? I think square root of 3. And y should be -1. Okay, so that dot is supposed to be go to pi over 6 and walk the wrong way 2 units. Good. And it's at 7 pi over 6 like we talked about before, and radius 2. Okay, now if you want to go the other way, if you have a rectangular point, and I think there's one given, it's the one we're given is kind of gross, but that's okay. It says convert from rectangular to polar. So it has 4, 5 out in space, and that's where it should be. That's the rectangular version, and I want to figure out what the polar version would be. And I'm not going to plot the polar version because it's kind of hard to do in Desmos, but it's got, you can tell it's got some sort of gross angle, right, and kind of a gross radius. So we'll struggle to find that, but that's okay. Well, I'm going to use these formulas. So tangent theta should be 5 over 4. Well, that means you need to take arctan. And that number, let's go ahead and get that number, is going to be a radian. And it's positive radian, and it should be between 0 and pi over 2. Let's remind ourselves what pi over 2 is. Okay, so that is the right quadrant. Remember, arctan and arcsine only take things from certain quadrants, so you do need to check when you do an arctangent that you're in the right space. You can definitely end up in the wrong quadrant. Okay, so that's my angle. That is an angle. It's in radians. It just doesn't have a pi in it. And then my radius, well, it should be 4 squared plus 5 squared equals r squared. And so I need to take the square root of this. So I guess the square root of 41. Okay, so this should be, I'm using this equation up here with the r squared in it. Pythagorean theorem, basically. Okay, so my point then, r would be square root 41, and my angle would be 0.896. Okay, obviously ignore the point over there. That is not the real point, but this is how you would write that in polar, and that's pretty nasty. So let's go ahead and do this one more time with a simpler point. So we'll do all the same things, but we'll use a simpler point to get our point across. Ha ha. Let's see, what's an easier one? I think this shouldn't be too hard. Okay, yeah. So you can actually cheat a little bit here. We'll do the formulas, but you can actually cheat and use the polar grid. You can tell that that is the angle's the angle's pi over 3, and the radius is 2. But let's do the formulas anyway. So if you take arctan, and then y is root 3, and x is 1, you get that angle. That pi over 2 is 1.5 something, so that makes sense. But really, doing this in Desmos doesn't tell you that that's pi over 3. However, the grid does tell you it's pi over 3. And then if I want the radius, x is 1 squared, and then square root 3 squared. That's really 4, so take the square root of that to get 2. So r should be 2. So let's see, our final point then, in polar, not in rectangular, would be this spot. And again, I'm graphing a rectangular plot, so ignore that spot. Even when Desmos has the polar grid, it will think you're plotting rectangular points, which is pretty annoying. However, one cool thing Desmos does, we're not going to look at some graphs, is that it will graph polar graphs even though it won't do polar points. So let's get rid of all this, and let's use our polar axes here. And so if you have r as a function of theta, you get some graphs here. If you start with a basic one, and I'm just going to do all these at the bottom of page 62. R equals 3. Well, no matter what theta is, the radius is 3. That would be a circle, right? The next one, I can't do in Desmos. It gets upset, but if you do theta equals pi over 4, think about what that is. That means theta is constantly pi over 4. It doesn't matter what r is. R can be anything. That's going to be this line. It's actually the line y equals x. Okay, you go straight like that. The next one, r equals theta, is a pretty cool spiral. Now, why does this happen? For all these graphs, you're going to start in the middle and go around, and as theta moves, so as theta increases, r increases. So when you're at pi over 2, the radius should be pi over 2, but when the radius is, when the angle's pi, then the radius is bigger, and then so it keeps spinning out as the angles go around. And of course, the angles keep going, right? 2 pi, 4 pi, 6 pi, and so you get this infinite spiral. Pretty psychedelic. It goes on forever. Desmos is just getting upset and quitting on me. Okay, the next one was R equals cosine theta. This one's a little bit hard to explain. It's a circle, which is nice. So I'm going to show you the regular cosine graph. And think about what's happening here. This graph should start should have a radius of 1 when the angle's 0, so it starts here. And by the time you get to pi over 2, the angle already comes down to 0. So this happens to pi over 2. Now you have a negative radius. So what should happen in the second quadrant, I should go over here, happens on the opposite quadrant because that's how negative radius works. So in the third quadrant, the radius grows back to 1 and you complete the circle. Okay, well now you're supposed to be in the third quadrant, but you're still negative, so it flips over to the first quadrant and it starts tracing it again. And then the fourth quadrant's where it should be and finishes it. So this circle completes twice from 0 to 2 pi. That's why, notice here, it keeps giving me how long it needs for each of these. It says 0 to pi, not 2 pi. And if I can get this, I don't know if this will work. No. I don't think I can do the thing I did with parametric for polar points. But if I was to trace a little dot out, it would go all the way around once and then again. I generally don't use TI calculators in this class, but one advantage of graphing polar on a TI is that it'll do it slowly, and so you can see the graph peel out. I guess if I did this might work. If I make a slider. How do I make it be a slider? Okay, there we go. Okay, so if you start B at 0, and you can see that by the time I get to about 3.14, it's already done, and then it'll go around again, although you can't see it happen again. We'll keep that slider out if we need it. Get rid of this guy. Okay, so that's R equals cosine theta. The next one is R equals 1 plus cosine theta, and this is called a cardioid. It looks like a heart if you turn it sideways. Now, if you think about y equals 1 plus cosine x, the key thing to remember here is that this graph is never, from 0 to 2 pi, this graph is never negative. So you start out with a radius of 2. By the time you get to pi over 2, the radius is 1, and then the radius doesn't hit 0 until you're at 3 pi over 2. So you're over here, you're at pi. And then the radius grows back and it comes back to 2 by the time you're back around. And you can see the symmetry around pi here. That's why this graph is symmetric. So that one's a little nicer. That's called a cardioid. And you can see here it goes to 2 pi. If I leave that blank up here, it does auto-populates that with pi, but 2 pi here. Okay, one more weird one, and then we'll extend this idea. Now I get petals for cosine 2 theta. And by the way, all these sine graphs look just rotated. They're very similar. If I write y equals 2x, now my negatives are happening twice as fast. So starting here, by pi over 4, I'm already at 0. And then I'm at negative radii, which means I actually flip to this quadrant. If you follow this thing, it goes... Let's see if I can do this. Here's my B. So it goes, using negative radii, it goes down here, and then it flips around there. You don't have to study this too much, but basically it doesn't go in the order you expect it to, because the negative part of this makes it flip kind of to and fro. And then if I want to change this is the graphs at the end, ask you about 3 theta, or 4 theta, or 5 theta, or 30 theta. These get pretty crazy. So one real cool advantage of polar graphs is you can do some crazy stuff that wouldn't be possible. You could never graph that in a rectangular mode. I mean, you could, but I would not recommend it. So here, just make you guys trip out for a minute and show you some different, look at all these different graphs you can make so easily in polar. So that's one of the big advantages of polar mode. All right. So that's how you graph polar coordinates and polar graphs. So what we want to do now is we want to do area and derivatives and arc length. So now we're moving on to the second half of the assignment. Now, area, I normally draw this out on the board, but I'm just going to give you the formula. If you do some Googling and look up sector of a circle, sector of a circle. The general way you do that is it is 1/2 r squared theta. And so if you think about like a slice of pizza, that is what I mean by a sector of a circle. So this is really area of a sector of a circle. If you think about it this way, if the area is pi r squared if it's the whole thing. So if theta is 2 pi, then you would get pi r squared, right? Which is what you're supposed to get for area of a circle. If you had an 1/8 slice of pizza, that would be, how much of an angle would that be? Well, it wouldn't be 2 pi around, it'd be 1/8 of that, so it'd be pi over 4. It'd be 1/8 of the whole area, so it'd be 1/8 pi r squared. And if you compare those, this number is half of that number, this number is half of that number. That's where that 1/2 is coming from. So think about it about pizza pieces and how much area you have. That's the idea. What we're going to do, though, is when we're trying to do the area, so let me give you a curve and an example. So if you do like r equals theta, let's see if this will work. This does not work for negative radius, so don't always, so be careful when you do this. Let me make that slider again. Okay, we're good to go now. See what it's doing here? When I start with a radius of 0, what this is doing is it's taking area up into the angle. Excuse me, guys. It's doing the area up into the angle here, and so at say like pi over 3, if I get or close to that, it's kind of making a straight arc here. This is a sector, but it's not a sector of a circle because the radius is constantly changing. But it's the same idea as a sector of a circle. And so we're doing little slices of angles to do this kind of sweeping motion. So our integral is going to be still 1/2 r squared, but not theta. It's going to be d theta because we're doing little tiny angles. If you go tight enough so that this looks like the edge of a circle, then you have a sector of a circle, just like we did the other types of slicing before. So then you're going to have 2 thetas here, theta 1 and theta 2. And this is going to be pretty straightforward because r is usually in terms of theta in the equation, so it should work out all right. So we're going to go ahead and get some examples from before. And we're at the point where you've passed your integral gateway. You can use technology to do this. It's more about setting these up. So even this integral here, let's say I want to go to 2 pi, and I want this area. Well, r is equal to theta for that curve, right? The less than or equal to is to show you the shaded area, right? This is r equals theta. I'm saying 0 to 2 pi. And I want 1/2, and then theta would be the thing I square, d theta, and that would be the amount. Whatever that number is, that's this area here. If I wanted to do, let's do cosine theta and see this graph. Let's try that one, because we should expect this thing has center at 1/2 and has a radius of 1/2. I think we should expect pi over 4 is the answer. So let's try that. So same idea here. There's no derivative. The most complicated thing about this is don't confuse this with volumes of revolution. It's a 1/2 r squared, not pi r squared, and it's d theta. So it looks very similar to the pi r squared formula. All I would do here different is, first off, this goes to pi. Remember that when I use equals here? This graph, if I get rid of this, Desmond says, hey, you only need to go to pi, right? We talked about that. So I need to go 0 to pi, or I'd have twice the area and it would be wrong. So cosine theta. And it's that number, which I guessed was pi over 4. Good. I didn't guess. I knew. Okay, so that's the idea of area. Okay, now your derivatives are kind of convoluted, and there's the idea of a dy dx integral, or sorry, derivative, is just like we did for parametric, where you're going to put dy dx equals r dy d theta over dx d theta, just like we did with dt. And that's great, but theta is usually connected to r. So how do I do this? Well, first, it's complicated, because first you have to do y equals r sine theta, right? X equals r cosine theta. Then you have to use r as some function of theta. You have to sub that into R, then you get X and Y. I don't remember if I asked you any problems on this, but it's a pretty big mess. It's doable. It's gross. There's some great examples in your book at 8.3. And then your book gives you an arc length formula that is really nasty. And then one of the last problems in the section says, hey, you can actually do it way easier if you do it this way instead. So I'm going to give you that version of arc length. And so you can mostly skip this. There might be one or two web assigned questions about this version of derivative, but you don't need it for arc length. If you want to do arc length of a polar curve, in fact, we'll do this one. And here we know the radius is a half. So again, thinking about what this should be, it should be 2 pi r. R is 1/2. So pi should be the answer to the arc length for this formula, for this circle. Okay, so the arc length formula is this. Let me make a note. Arc length of a polar curve. Okay, you still need it up with two squares like you normally have been. So you have theta 1 and theta 2. It's going to be in terms of theta. And it's going to be r squared plus dr d theta squared. So whereas the arc length for functions was 1 plus the function squared, now it's the function squared plus the derivative squared. So for this one here, r is cosine. So this cosine goes here. The derivative of cosine, last time I checked, was negative sine, although we're going to square it. And the thetas are 0 to pi. Remember that for this particular curve, we only go to pi. And pi was the answer, which is what we expected for the arc length, or the circumference. Let's do one more so that you get the idea for that. R equals theta was another spiral we're looking at. Let's do 0 to 2 pi for this one. Let's just go to 2 pi. How long is that curve? Well, it would be the same idea as this, but theta is the function and the derivative is 1, except I'm asking to go to 2 pi, so I would get this answer. By the way, that's a trig sub yet again. Okay, so that's everything we want to do for polar coordinates. If you have questions, please talk to me on Discord or email me. And I hope you have a good end of the semester as best you can. See you guys around.